Hi, my name is Saad. I'm a software engineer at Google and I work on the storage stack of Kubernetes. Today I'm going to talk about storage classes and dynamic volume provisioning, a new feature in Kubernetes. First, I'll introduce these concepts and then my colleague Matt will walk you through a demo on GKE. Let's start by identifying what problems Kubernetes volume plugins are aiming to solve. First is that the basic unit of scheduling in Kubernetes is a pod, which is a collection of containers. Containers do not share their file system, but pods are composed of possibly multiple containers. This could be, for example, a reader and a writer container that work together. So it would be really nice to be able to share files between containers in a pod. Second problem is that containers are ephemeral, and the files inside a container are also ephemeral, meaning they're deleted when the container is terminated. This means if a container crashes or the machine is restarted, you lose your data inside the container. If you're trying to run a stateful service, having your data disappear is a non-starter. This is where Kubernetes volumes come in. At its core, a volume is just a directory, possibly with some data pre-populated in it, which is accessible to all the containers in a pod. How that directory comes to be, the medium that backs it, its content, what happens to it after the pod is terminated are all determined by the particular volume type used. Okay, let's take a look at the volume plugins we have in Kubernetes. The plugins can be categorized into a few large buckets. One class of volumes is persistent network attached storage. These are volumes that outlive the life cycle of a pod. This could be anything from NFS share to a cloud provider virtual disk. The life cycle of these volumes is independent from the life cycle of an individual pod. When a pod referencing one of these volumes is created, the storage is automatically made available inside the container of that pod. The volumes are automatically attached and mounted. When the pod is terminated, the volume is automatically unmounted and detached if needed. But the data on the volume remains intact, and that's the key. The data is persisted. If another pod comes along and references the same instance of the volume, they'll see the same exact data. Another class of volumes is ephemeral. These volumes are created when a pod starts and is deleted when a pod is terminated. Empty dir is the prime example here. It is shared scratch space between pods. Kubernetes creates an empty directory on the underlying node machine, either from the local disk or from an in-memory tempfs. And it mounts the directory into all the containers in the pod. Then when the containers start, they have some shared scratch space between them. When the pod is terminated, the directory and its content is deleted. Secret, config map, and downward API are concepts in the Kubernetes API. They are mechanisms for sharing configuration and cluster information with applications. One of the core principles of Kubernetes is to meet the users where they are. This means that instead of requiring applications to talk the Kubernetes API, we try to make the data available in the form that applications already know how to consume. So while existing apps won't necessarily know how to talk the Kubernetes API, they can probably already read config info from a file. And so secret, config map, and downward API volumes are a mechanism for exposing these Kubernetes API objects as files inside the container of a pod. These volumes are essentially an empty dir under the cover, but pre-populated with the contents of the Kubernetes API server on creation instead of being empty. Now let's take a look at an example. Here we have a pod. A pod is a basic unit of scheduling in Kubernetes. Pods are a collection of containers, or in this case, a single busybox container that doesn't really do anything but sleep on startup. This pod directly references a Google Compute Engine persistent disk volume called Panda Disk for use by all the containers in this pod. The volume is assumed to already exist. The pod also defines where inside the container the volume should be mounted. Now, this example seems pretty trivial, but the real beauty is what happens under the covers. When the pod is created, Kubernetes automatically calls out to the Google Cloud API and attaches the specified PD to the node that the pod is scheduled to. It then formats the disk if needed and mounts it into the container that makes up the pod. When the pod is moved to another node, Kubernetes automatically calls out to the Google Cloud API, detaches the persistent disk from the first node, and attaches it to the second node, and repeats the same song and dance to mount the volume inside the new instance of the pod on the second node. All of this happens invisibly for the user and makes it so that they don't have to worry about what machine the workload actually landed on. Kubernetes just takes care of it. But there's something not quite right here. Let's take a step back and talk about a really nice design principle that many of you are probably familiar with, the separation of concerns. It says that the components managing distinct functionality should themselves be separated. This enables you to isolate, revise, and test components independently. It allows you to make your larger system modular so that you can swap out pieces without affecting other components. And Kubernetes does exactly that. It takes functionality that used to be smeared across various layers and handles them explicitly. It decouples the application layer from the cluster resources required to run applications. That means as an application developer, you don't have to worry about the implementation details of the cluster your workload is running on anymore. You don't have to worry about which particular machine your app is running on. You don't have to worry about whether that machine has enough ports. You don't have to worry about what other apps are running on that machine. Kubernetes abstracts all of that away and exposes an API that allows you as an application developer to simply describe the service you want to run along with the resources it will require. Kubernetes takes care of the rest. If you think about it, Kubernetes in this regard is very much like an operating system for clusters. Think back to the earliest days of computers when there were no operating systems, and every program needed a full hardware spec to perform even the basic tasks. Distributed system application development has been in this stage for a long time. And now Kubernetes finally introduces an abstraction layer that hides the implementation details and complexity of cluster implementation. The real beauty of an abstraction layer is that it allows you to swap out the components underneath it. It enables portability. You can run Kubernetes on a lot of different environments, everything from cloud providers like Google Cloud, AWS, and even on bare metal on-prem clusters, all with a consistent API. This decoupling of application from cluster allows applications to be cloud provider agnostic and not worry about network model, load balancing, persistent storage. This is great for you as an application developer because it allows you to write your applications, services, deployment descriptions once and have them work regardless of the underlying cluster. It helps avoid vendor lock-in. Now that's a really pretty picture I just painted, but for those of you who are paying attention, you probably are asking, didn't your pod definition specify exactly the type of volume to use for persistent storage? You specified a GCE PD with the name Panda disk. Now if you take that pod description and drop it on a non-GCE cluster, it's not going to work, right? You would be absolutely right. This is where the Kubernetes concept of persistent volume and persistent volume claim objects comes into the picture. Persistent volume and persistent volume claim objects enable an abstraction between the consumption of storage and the implementation of storage. The persistent volume object is a representation of a piece of storage available on the cluster, and the persistent volume claim is a request for storage on behalf of an application trying to run on the cluster. Let's take a look at an example. First, we have to expose the storage available for the application to use. We do this by creating a PV object to represent each piece of storage available for applications to use on the cluster. Each persistent volume object contains a description of the storage it exposes and connection information. Normally, cluster or storage administrators create these PV objects, not application developers. Once these PV objects are created, they are available for use. Now, if an application developer wants to use storage on this cluster, they must first create a request for storage. This is done by creating a PVC object. In the PVC object, you define the minimum requirements for the storage you need, the minimum disk capacity, and the required access modes. When the PVC object is created, Kubernetes takes the request and matches it with an available unbound PV. In this case, it finds one of the PV objects that we created earlier, a 100 GB GCE PD, is available and unbound. So it binds this to the request, the PVC. Now this claim can be used by the application developer. Let's go back to the pod definition we used earlier. In order to use the storage, you can now reference the claim for storage, instead of directly referencing a specific volume. The beauty of this is that our pod definition is now portable. The request for storage resources is decoupled from the specific implementation of storage. We can take this pod definition and drop it on any Kubernetes cluster, and as long as there is available storage, it will just work. And even if you're running only on a single cluster, it means that your cluster administrator can completely swap out or modify the storage system in your cluster, but your pod definitions won't need to change. So the persistent volume and persistent volume claim abstraction is really nice for giving us portability. But you probably noticed that there was a step in there that was a little cumbersome. Having a cluster admin or storage provider pre-provision all the volumes available for use in the cluster. This is where dynamic volume provisioning comes in. This is a feature that is unique to Kubernetes. The idea is that when a request for storage is created, when a PVC is created, the cluster automatically creates a new piece of storage to fulfill that request. This makes a lot of sense in cloud environments like GKE, where an API call can provision new storage within a matter of seconds. But even for non-cloud storage systems like NFS, you could write a provisioner that maybe triggers the creation of a new share on demand. To use dynamic provisioning, the cluster storage admin must first enable it. They do this by creating one or more storage class objects. The storage class object specifies the volume plugin to use for provisioning and the parameters to pass to that plugin. The parameters for the storage class are a blob of key value pairs that the provisioner presumably understands. In this case, the first storage class says, when executed, call the GCE PD volume plugin and pass in parameters to create a standard spinning disk. The second storage class pretty much says the same thing, but instead passes in parameters to create an SSD GCE PD. The parameters are defined by the volume plugin and set by cluster admins, and are opaque to Kubernetes otherwise. What's really neat about that is that since the parameter list is a blob that is passed through to the provisioner, Kubernetes doesn't have to get into the business of enumerating every possible parameter for every storage system in its API. Plugins expose an arbitrary set of knobs for disk provisioning, and cluster admins can tweak them at will. Cluster admins can define multiple storage classes to expose different tiers or groupings of storage to cluster users, and users don't have to worry about the details. So in this case, the cluster admin exposed what they called fast and slow storage, and application developers don't have to worry about the details of what that means under the covers. They just pick from the storage classes that are exposed to them. To use storage, just as before, the application developer creates a persistent volume claim object to request storage. In the persistent volume claim object, they now specify the storage class to use. In Kubernetes 1.6, this is a new field in the PVC object. In earlier versions, this was an annotation on the PVC object. When a PVC object with a storage class is created, instead of binding to an existing available PV, Kubernetes calls the provisioner defined in the specified storage class to create a new volume. In this case, it calls the GCE PD plugin, which calls out to the GCE API to create a new SSD-backed GCE PD. Once the new storage volume is provisioned, Kubernetes automatically creates a PV object to represent the new storage, and then binds it to the user's persistent volume claim. It's important to note that dynamically provisioned volumes are created with a delete retention policy. That means once the PVC is deleted, the dynamically provisioned volume will automatically be deleted. If you don't want that to happen, you should update the persistent volume object after it is automatically created and change the retention policy to retain instead of delete. Once the new volume is created and bound to the PVC, users can reference the PVC in their pod definitions exactly the same way. Something else to keep in mind is that storage classes can be marked as default. Marking a storage class as default makes it so that even a PVC without a storage class specified will trigger provisioning, instead of binding to an existing pool of PVs. This is a mechanism for cluster admins to force dynamic provisioning. Also important to note is that Kubernetes 1.6 will come with the storage class pre-installed and set as default for GKE and other cloud providers. This is something to pay attention to if you've been using Kubernetes for a while, because it changes the default behavior of PVC objects on these clouds. It used to be that PVC objects without storage classes would bind to available existing PV objects. But on these clouds with 1.6, because there will be pre-installed default storage class, a PVC without a storage class will still trigger the creation of a new volume. If you want to disable this behavior, you'll have to modify the storage class and remove the default annotation. Now I'm going to hand it over to Matt to demo this.
Thank you, Saad. My name is Matthew DeLeo. I'm a product manager for Kubernetes and GKE, and I work on networking and storage. Today I'm going to be doing a couple demos for you. The first is a demo of how to manually provision and use a disk inside GKE, and the second will use the dynamic provisioning feature that Saad talked about earlier. So let's jump right in. I've already created a cluster. It has 3 nodes in it, and each one of them has 1 virtual CPU. I'm using version 1.53 of Kubernetes, so it's going to use the annotation that Saad mentioned earlier rather than the built-in storage class things that we introduced in 1.6. So going back to my terminal screen, I'm going to run this demo. And just to see that there's no other disks inside GKE, I'm going to run this gcloud command. And from here we can see that there's just 3 disks. These correspond to the 3 nodes that I have in my cluster. And now we're going to check to make sure that there's no physical volumes, PVs, and there's also no PVCs, physical volume claims. Next, I will use gcloud to create a new disk inside Google Cloud Platform, and I will call it manual disk 1. That's step number 1. Next, we're going to make sure it exists. So we're going to run the gcloud command to list the disks that we have. And we can see that we have our 3 node disks. And now we also have manual disk 1. Next, we're going to add a corresponding physical volume to Kubernetes. So I've just created a simple YAML file that lists the name of the actual disk that I want to use. That's the PD name down at the bottom here. And that says manual disk 1. Then I'm going to give it a name. I'm going to call it manually created PV. I have a capacity that's set to 10 gigabytes, and I've set the reclaim policy to be retain. So I'm going to load that into Kubernetes. So that's in now. And now we're going to make sure it exists. So I'm running the kubectl get PV, and that'll list the disk that we have, and we can see that it exists. We have 10 gigabytes available. The reclaim policy is what we expect it to be, which is retain, and it's 4 seconds old. Now we're going to go ahead and create a physical volume claim by asking for 10 gigabytes of storage. We're going to call it my PVC, and we're going to go ahead now and load that into Kubernetes. So at this point, we should have a PV and we should have a PVC, and the PV should be bound to the PVC. So we're going to check that real quick. I've listed both the PVs, the physical volumes, and the PVCs, the physical volume claims. Now in the first couple lines, you see that we have a bound PV. It's bound to, has a claim of demos/myPVC. And in the last 2 lines, we have myPVC, and it's bound to manually created PV. The final step is to use this physical volume claim in a pod. And so here we are, we've referenced the claim name. That's in this line under volumes. And we're going ahead and creating a new pod. It's called Sleepy Pod. It doesn't do much. It just sleeps for 100 minutes and then goes to sleep. So we've gone ahead and created that. It's going to take a few seconds to warm up and actually create the pod. And so while we're waiting, we're just going to check on it. Looks like it's running now. So I'm going to go ahead and show you what happens when you want to tear down one of these setups. So the first thing you need to do is delete the pod. At this point, you still have a PVC and a PV, and those are still bound to each other. And while we're waiting for that pod to delete, it takes a few seconds for the pod to delete, but once it's done, we should be able to see, at this point, our pod is deleted. Now we're going to go ahead and delete the PVC and also delete the PV. So as you can see, I've just checked to make sure that there's no PV and PVC resources. And now I need to actually delete the disk in Google Cloud Platform. So I ran the gcloud command to do that. So that's it. There's 4 steps of manually provisioning a physical volume and using it in Kubernetes. The first step is to go ahead and create the volume in Google Cloud. The second step is to create a PV object in Kubernetes. Then you need to create a PVC object, a physical volume claim in Kubernetes, and then you can finally use it in a pod. Next, I'll show how we can use dynamic volume provisioning to make this process a lot easier. And so I'm going to go ahead and start up my demo. And Here, just to show again that there's nothing going on behind the scenes, I've got a list of all my disks. We have, again, 3 nodes, 3 disks corresponding to those 3 nodes, and no other disks available in the system. Next, I'm going to go ahead and show that there's no storage classes that we've already loaded into the system. As you can see, there's none. And finally, we're going to make sure that there's no physical volumes or physical volume claims that exist in Kubernetes. So we have a pretty vanilla system right here. We haven't done anything yet. The first step is to add storage classes. And so what I've got here is a YAML file. It's very simple. Because I'm using 1.5.2, it still is in beta. But when it goes to 1.6, this will no longer be a beta API object. I'm going to create this storage class. Its type name is fast. Its type is SSD. And we're going to use the GCE PD provisioner, which you can see is all listed here in the YAML file. So we'll go ahead and load that into Kubernetes. Next, we're going to go ahead and list the storage classes so we can see that we have the fast type of storage. And we can see that it's the GCE PD type. Now, we just have to add a PVC. So this one's a little bit different than what we had when we were manually provisioning our storage. This one has an annotation. Again, the annotation will be different when we switch to 1.6, but right now we're on 1.5. And I just have to add the annotation that say I want the storage class set to fast. And I say that I want 10 gigabytes. And once I create this PVC, what it's going to do, it's going to go ahead and provision the storage on Google Cloud Platform, and it's going to create a bind to that storage object. So to see that, we can go ahead and list the disks, and you can see that we have a new disk here. It's at the very top of the list. It's a 10 gigabyte, and its type is SSD, just as we expected when we created the storage class. It's very simple to now use the PVC in the pod.yaml file. This is actually the exact same YAML file I used earlier in the manually provisioned example. So let's go ahead and load that into Kubernetes. At this point, the disk has already been created, and we just need to start up the pod. Great. So now it's running. We'll go ahead and just show the deletion path. So now I want to delete the pod. Again, I just delete the pod as before. It'll take some time for the pod to actually shut down and terminate. Now the pod is shut down. I'm going to go ahead and run a gcloud compute disks list, and this will show us all the disks that we still have in our system. As you can see from here, we still have a PVC backed storage that was dynamically provisioned, and its size is still 10 gig, as we'd expect. I'm going to go ahead and delete the PVC. When I do that, I would expect the PV, the actual backing disk, to be deleted. If we go ahead and check that, now we can see that it's actually deleted. So there you have it. To use dynamic volume provisioning, all you have to do is create a storage class, create a volume claim, and then use the volume claim. And so as you can see, dynamic storage provisioning makes it a lot easier. We only had to allocate a storage class type, and we can use it everywhere. That's it for the demo. Thank you very much, and I'll turn it back to Saad now.
Thank you, Matt, for that demo. So that's an overview of dynamic provisioning and storage classes in GKE, a unique feature in Kubernetes that enables storage to be created automatically when it's needed. Thank you for joining us. To get involved or to learn more, visit us at the Storage SIG. To try Container Engine, use this code for a free trial account.